One last item we're going to discuss regarding our dielectric interfaces is refraction at the interface. And so what this is we have our sort of same drawing here for our two regions with different dielectric constants. And so maybe we have some electric field E2 in our region 2 that looks like this, but then once it goes into our next region, maybe it has sort of a different angle with the normal, so it looks something like this. So this would be our E1, and this would be our E2. And so what we want to figure out is sort of what is the relationship between that change in trajectory. And so we're not going to go through the derivation of that. I'll mention where it is in the textbook, but let's at least sort of set up what the problem looks like here. So we can, of course, decompose this into our normal and tangential components. So we essentially have these right triangles. And so I've drawn this sort of exaggerated, and we'll see it depends on our material properties as to how far that electric field refracts. So let's see, here we have our E2, so this would be our normal component of E2 down here directed this way, and we would also have our tangential component of E2, so E2 tangential. And then same thing up here, we have our normal component of E1, so E1 normal, and our tangential component of E1, E1t. All right, and so let's say we define this angle between our E2 and our E2 normal as being theta 2. Okay, so and then the angle for our region 1, which is going to be defined between some sort of line here, and let me align that a little better. So this would be aligned with that normal component of E2. So we could say some angle there between that line and our E1 is theta 1. And so that turns out that that's going to be, through geometry, we can say that's the same angle theta 1 as between this E1 and our E1 normal. And so again, we're not going to go through sort of the derivation of this, but with some geometry, what we could show is that the ratio of those tangents, so tan of theta 1 divided by tan of theta 2, is equal to the ratio of our dielectric constants. So we have epsilon R1 divided by epsilon R2. And so again, there's a bit of a proof or derivation to go through to get to that. We're not going to look at that, but if you're curious about what that is, you can look on pages 200 to 201 of the textbook. One important thing to mention, though, is in deriving this equation, we've made one assumption, and that is that the surface, or the interface, is free of charge. So interface free of charge. And so basically, we can see that based on the material properties, the relative permittivity, or the dielectric constant, is going to determine how much the fields are deflected as they're moving between the two regions.